Okay. All right. Yeah, I guess before we get started with stuff today, I just wanted to check in and see how you guys are doing, how the homework's coming along. Are there questions regarding any of the content we've covered so far? So last week we had inverse CDF and I forget. Rejection sampling, and then on Tuesday we covered kind of some things based on the definitions and convolutions, and so you might have to look up some of the relationships between distributions. You might have to look that up, and then we also looked at the bivariate normal. Doing something like that. Okay, and then the last problem in the homework is on Monte Carlo integration, or basically estimating the value of an integral, or whatever it might be based on Monte Carlo estimates. Okay, and so this is the problem. You can try this out. You could run it through Wolfram Alpha to get kind of a numeric value that Wolfram Alpha evaluates, and you can compare that to what your Monte Carlo estimates are, things like that. Are there questions? Do we feel okay about all of this? Okay. All right, then in that case, we'll continue on. So we have I just want to cover a little bit more about Monte Carlo integration. Okay, and we said that we have that the Monte Carlo estimator is h bar sub n, okay? And this is equivalent, or this is defined as the sample mean of the values okay, so this is the sample mean of the function h of x where sample mean of the function h of x applied to random values, applied to random draws of x. Okay. And so this becomes the estimated value or the expected value of h of x over where x is defined by the PDF of f, okay? And so, by definition, this is equal to the integral over the domain of h of x multiplied by f of x. Okay. Domain or support of x, we'll say x comes from f of x, okay? And we can say that can be estimated h bar sub n, okay? So the expected value of this function can be estimated with the Monte Carlo estimator. So this is what we covered on Tuesday. Right, and we said if we have a function so this can be used to estimate the area of an integral, or this it can be used to estimate the average value of a function. All right, so let's say you have some function h of x, which looks like this, or something like that, right? And this goes from a to b, okay? So we can say the integral I is equal to a to b of h of x dx, okay? And we can say that the integral I is equal to the area under the curve which is technically also equal to, if we find the average value of the function, like maybe something, so if we say, this right here, this could be that height, and we can say that the area of the integral we can say the integral is equal to b minus a times the expected value of h of x. Okay. So this, whatever height this is, we can say, the two areas are equal if, if one is the kind of the average of the function, average value of the function, over the interval. right? And so, so in this case, this is going to be the expected value over f, where f is going to be x comes from f of x, where f of x is equal to the uniform distribution over a from a to b. Is that okay? All right, and thus we can estimate the area of the integral, estimate, I guess, the value of the integral, with the estimate of I will just be b minus a, and we will plug in h bar sub n, okay? Or again, h bar sub n, is 1 over n times the sum of h of x of I. Okay, and then our x of i's are random draws from the uniform distribution from A to B. Right. Is this okay? Okay, so I mean, we'll just do a simple example. Okay, so let's say we want to integrate from 0 to 2 pi. We'll do cosine x plus 3 dx, okay? So we'll go 0 to pi to 2 pi. This is in radians, right? And so where do we start off? Cosine of 0 is at 1, so 4. So we go up to 4, and then I think it looks like that, right? All right, and the question is, what's the area here, right? Okay, and then so my favorite thing, right? Wolfram alpha. We can always just say integral from 0 to 2 pi of cosine x plus 3 dx. All right, let's see if it computes. Okay, and so we have this. This is our picture, and it says we get 18.85, about a total area of 6 pi. 6 pi about 18.85. Okay, so our answer is around 6 pi around 18.885. Okay, let's do the Monte Carlo approach. Okay. So what we have is we want to estimate I, okay, and I is equal to b minus a times the expected value of h of x, right? This is what we have, okay? And then, so this is going to be b minus a, and the expected value of h of x is the integral of h of x times f of x dx, okay? And then we can replace that and say this is going to be approximately equal to b minus a times our Monte Carlo estimator, okay? And so our h of x is going to be this function, cosine of x plus 3. And then what is our f of x? F of x is, we're going to just use the uniform distribution. The uniform distribution from where? From 0 to 2 pi. Okay. So f of x is the uniform distribution from 0 to 2 pi. All right. And so f of x will be equal to the function for f of x is 1 over 2 pi, right? Because the total area of f of x must equal 1, right? So the function here is going to be that. Okay, so what we will do is we draw x sub i's from uniform 0 to 2 pi. We apply h of x to the x sub i's, and then we take the mean of h of xi's, which is going to be our h bar sub n, and then we multiply h bar sub n by b minus a. And we hope at the end of all of this we get something around 18.85. Is that okay? All right, so let's try that out with R. Okay, so we'll say our x is going to be R unit. We'll ask for a million of these, and so R unit, you can set the min and the max. So we're going to ask for a million of these. The min will be 0, and the max will be 2 times pi. Okay, and so I've got a million elements. It's done. All right, h is a function of x, and what it will do is it's going to find the cosine of x plus 3. We're going to ask for cosine of x plus 3, right? Okay, and then so I'll just have hx, which will be h applied to x. All right, so now I've got a million hx's, all right, and then let's just ask for the mean of hx. And I guess this will be our hn. And then our I hat is going to be b minus a, right? So 2 times pi minus 0 times hn. Okay, and what is our estimate I hat? We have 18.854, which is pretty good of our the true value. Okay, and so this is, I don't know, that's it. That's Monte Carlo integration. Okay, so we can get the estimated value of a function, just these 5 lines of code. I'll go ahead and throw that in here. And you know, and this will work. Okay. We can let's see. All right, we can do something. Well, let me just pause here and just make sure this is okay. All right. So, are there any questions on this? No, we're all good. Okay. All right. So that's Monte Carlo integration, and we can further expand this. And I think you've got a example in your homework to do this. Okay, using the uniform. Now, sometimes if there is significant mismatch between this distribution, the f of x, and you know, whatever function it is, you know, your estimates will not do a great job. Okay, and we covered other methods. We said, you know, maybe we have another function, right? So this was using f of x being a uniform, but technically f of x can be from any distribution. Okay, so you know, what if the values weren't being drawn, you know, uniformly across something? Then we get something else, right? So again, you know, Monte Carlo estimation can be used for any distribution f of x, okay? And then the estimate will then be, you know, the estimate of okay. So for example, you know, f of x can be standard normal, and this was the example that I first did, and h of x could be x to the 4th power, right? And we could ask, what is the expected value of h of x if x is drawn from standard normal? Okay. Well, the true answer, the expected value of f of h of x, is going to be the integral over the domain. So that would be technically from minus infinity to infinity of x to the 4th times f of x dx. Okay? We're going to estimate this using h bar sub n, which is just going to be h applied to x of i's, where x of I is now drawn from the standard normal. Okay, and we did this example. This will be Step 1 is draw x super I from standard normal. Then apply h of x, and then take the sample mean. So Monte Carlo estimation can be applied to kind of get any other value, right? Any other function, any other distribution. And so in this example, we're going to just say x will be our norm, and we'll ask for a million values. H will be a function of x, and that we just raise it to the 4th power. And then hx will be h of x, and hn will be the mean of hx. Okay, and let's just see what hn is. Okay, and we get something around 3. And that's that. No big deal. And then if we wanted to, estimate the variance, all we have to do is we just take the variance of these values, hn, also. Okay. Okay, we could run into a situation where the f of x is a difficult function or something, right? So now I'm going to introduce something called importance sampling. The concept is called importance sampling, but I like to say, I think a better name would be weighted Monte Carlo estimation. So far we've just been doing Monte Carlo estimation, and this is just a weighted version of it, okay? But for whatever reason in the literature, this is called importance sampling, okay? But I feel like importance sampling gives the wrong idea. We're not using this to create a sample of values like rejection sampling. Rejection sampling, you're getting a sample of values. Here, we're still estimating the expected value of some function or something like that, okay? So, we still want to estimate so this is still the same task that we want to do. We still want to get this value, the expected value of a function h of x, if it's applied to some random variable defined by the PDF f of x. Okay, so we're doing the same task. We want to get, what is the estimated value of h of x if we apply it to some PDF f of x. Okay, and so this is still defined as h of x multiplied by the PDF f of x dx. Okay, so this is our function over here, h of x, and over here f of x, this is a PDF. Okay, and in our examples so far, f of x was easy to sample from. Okay, so one example was f of x was uniform, or f of x is the normal distribution or something like that. Okay, but we could run into a situation where we have a function h of x and we want to apply it to a random variable, but the random variable itself is, for whatever reason, is difficult to sample from directly. Okay, so imagine a new scenario. Where it is difficult for us to get a random sample drawn from f of x. Okay, so maybe f of x this time has some unusual form, and it's difficult for us to get a random sample drawn from f of x. Okay, and so when we ask, what is the value of this function when we apply it to this random distribution, we can't just draw from the random distribution and apply the function and get the estimate. Okay, now we're in a situation where we can't draw from f of x. So what can we do instead? All right, well, we're just going to do the very best we can, and we are going to just sample from another distribution. Okay, so we'll just say, well, I can't get samples from f of x, so I'll just do what I know how to do. I'm going to get samples from g of x. Okay, so instead, we will just draw random samples from a different distribution g of x. Okay, there doesn't have to be a relationship between f of x and g of x. Okay, we get better performance if g of x looks kind of like f of x, but mathematically it will work out either way. Okay, so we just draw random samples from an entirely different distribution g of x. Okay, and so now we're in a situation we still want what is the estimate, the expected value of h of x if x is drawn from f. But now we're getting values drawn from g. Okay, and we don't want the expected value when values are drawn from g. We're just going to do this. Okay, so we will instead just draw samples from a different distribution g of x. Let me just say g of x can be any distribution. The only requirement can be any distribution. The only requirement is that the support of g of x has to be a superset of f of x, okay, of the support of f of x. So if f of x, the PDF for f of x goes from, let's say, 0 to 10, then the support of g of x has to at least contain 0 to 10. If it only goes from 0 to 5, it's no good, okay? So if it goes from 0 to 11, that's fine, all right? Or if g of x goes from negative infinity to infinity, that's fine, okay? Whatever it is, g of x can be any distribution. The only requirement is that its support support is a superset of the support of f of x. Okay. Okay, and so g of x is called the trial or candidate distribution. Okay. And so what we have now is we've got the expected value of f of h of x is, I'm going to just rewrite this. I've got h of x times f of x dx, but what I'm going to do is I'm going to multiply by 1 over g of x times g of x, okay? So this does not alter the value, right? Because I'm multiplying by g of x and 1 over g of x. Okay, so that's not going to alter the thing. And so what we can do is, instead of saying this is the function and the PDF, I'm going to break it apart like this, okay? So this will be our PDF. This is, we are able to sample from this, and this is going to be my function. Okay, so the expected value of h of x, where x is drawn from f, this becomes the expected value of h of x, I'm sorry, not h, will become the expected value of h of x times f of x divided by g of x, where x comes from the distribution g. Okay, so here we have, the expected value of a function if the function comes from this PDF. Now we have the expected value of this function if the x comes from this PDF, and that's what we have here. We have the expected value of h of x times f of x over g of x, where x comes from g, okay? Is that okay? And so this is kind of like a weight compensation to make up for the fact that we are drawing from g of x rather than f of x, okay? This term compensates for drawing from G rather than F. I hope you're able to read that. Okay, so let me put a little, I don't know, make an illustration up on the board, okay? So again, what we want is this, and we're going to say this is Okay, so this is I'd written all of this on the previous slide. Okay, and so this is x is drawn from g of x. Okay, so let's say we've got some PDF Okay, so this will be our PDF f of x, okay? PDF f of x, maybe it is difficult for us to draw a sample from it directly. Okay, so we've got some kind of function. It's difficult for us to get a sample of this thing directly. Okay, and so what we will do instead is we'll just say, all right, I've got another function that looks like this, okay? And so this will be a different distribution g of x. Different distribution g of x, and we're going to say we can get samples from here easily. Okay. So let's say like right here, let's say here I've got x x1 okay. So we can see that random values with this value x1 will get drawn twice as often from g of x than they should if we drew from f of x, right? So values at x1 will be drawn about twice as often if we draw from g of x instead of f of x, right? And so if we applied the function h of x to this, to x1, those values would appear too often, okay? So to compensate for that, we will we weight those values of h of x to be less by saying f of x is only half as tall as g of x, okay? So to make up for that, or to compensate, I should just say, all right, to compensate, we weight the values of h of x with the term f of x divided by g of x, which will be about, about half. Okay, so those values, when we draw x1, those values carry half the weight. Okay. Meanwhile, if I if we look at, values at x2, I should put this in, okay. Values at x2 will be drawn, I don't know, about, only, I don't know, 80% as often as it should. 80% as often if we draw from g of x instead of f of x. Okay, and so values at x2 are weighted more heavily. Okay, so f of x over g of x, is going to be greater than 1, maybe about 1.25-ish or something, right? Does that make sense? Okay, so we're going to just say, you know what? I don't know how to draw samples from this funny looking thing, f of x. Okay, so we just draw from g of x instead, and then we compensate for it using this weighting term, and that's what we do. Okay, and so again, so I guess our steps are just like before. Will be something like so we wish to estimate expected value of h of x over the random variable defined by f of x. Okay, we can't draw from f of x directly. Okay, so we draw x super i's from g of x. Okay, and then for each xi, we calculate h and f and g. Okay, so there's more calculations involved. We gotta calculate all of these things. All right, and then take the sample mean. Okay, and then so we get h bar sub n, which is just going to be equal to 1 over n times the sum from I equals 1 to n of this term. So we take the sample mean of all of this, and this is going to be approximately equal to the thing we want. even though we are drawing from G. So even though we're drawing from G, as long as we weight those values accordingly, we will get the correct estimate. Okay, let's try this out. All right, let's do an example. An example. Let's say we'll do our folded normal. Okay, so f of x is going to be, so our folded normal distribution is just the positive half of the normal distribution, right? Okay, and again, because it's only half of it and it still needs to integrate to 1, it's going to be 2 times the normal PDF for, you know, x on the interval 0 to infinity. Okay, so this is going to be 2 times 1 over root 2 pi e to the negative x squared over 2. Okay, and we will say we want the expected value of the PDF. Okay, so this is expected value of x as defined by f, and this is going to be the integral of x times our PDF, 2 times 1 over root 2 pi e to the negative x squared over 2 dx from 0 to infinity. Okay, so in this case, you know, h of x is just x, and f of x is equal to 2 times 1 over root 2 pi e to the negative x squared over 2. All right, so I mean, this is a silly example because we are able to get values drawn from this, okay? And so, you know, this is a, you know, a bit of a contrived example. Is a little silly because we can draw samples from f of x, right? All we have to do is just draw normal values and then take the absolute value of them, right? And we would be getting values from the folded normal, okay? Or, I mean, if you want to be really extreme, you can just throw away the negative values, okay? But you know, do you guys know what the expected value of this thing would be? If you only take, so the expected value of the normal is 0, because it's symmetric. But then if you only take positives, like if you take the absolute value of everything, and then you take the average of them, do we know what the expected value would be? It's not as straightforward, right? So, I mean, so the easiest way, right? So, folded normal. So the Monte Carlo approach is just saying, well, I don't know. I don't want to do math. I hate doing math. So we're just going to ask, we're going to just say, all right, let's draw 1,000,000 values from the random normal and then folded will be basically the absolute value of all of these things. And then let's just ask what's the mean of the folded values. Okay, and we get 0.7976. And we can ask for, what's the variance of the folded values, and we get this. Okay, maybe we're not so sure. We can say, all right, I want 10 million values. It takes a little bit longer, but it's not too hard. Okay, and we get 0.7979. Okay, I don't know. Is this a recognizable number? Is that square root of 2 over 2? I don't know. Maybe there's some significance here. But anyway, we're just getting some kind of numeric estimate here, right? So it's easy, right? So this is because we can draw samples from f of x. All we have to do is just say x is, I don't have to actually rewrite this. All right, so I'm going to just copy this. Okay. Okay. But we will pretend that we are not able to sample from f of x directly. Okay? We will pretend that we can't, just so we can apply importance sampling. Okay? So we pretend okay, so what do we do instead? All right, we have h of x, we have f of x. Okay, so h of x is x, f of x is 2 times 1 over root 2 pi e to the negative x squared over 2. Okay, and so what we can do is we can just we will sample from the exponential distribution. Okay. All right, and in this case, so the exponential is so we'll say g of x will be lambda e to the negative lambda x. And just to kind of get our terms to work a little bit better, we'll use lambda equal to 2. But I mean, we could use any lambda if we wanted to, right? But just so our terms will cancel out, a little bit nicer, we'll use lambda equals to 2. Okay, so we are able to get g of x from 2e to the negative 2x, okay? So here we've got the expected value of h of x applied to values drawn from f. This will be the integral from 0 to infinity of h of x times f of x dx. And this will become 0 to infinity of h of x times f of x over g of x times g of x dx, okay? So this becomes 0 to infinity, h of x is just x, f of x is 1 over root 2 pi e to the negative x squared over 2 divided by g of x, 2e to the negative 2x times g of x, 2e to the negative 2x. All right, so some terms cancel, and this will become the expected value of g expected value of h of x applied over the distribution g of x sorry, not this. Sorry, I got to throw all those terms in there. Okay, it's the expected value of that, and so just kind of cleaning up. That's what this part is, right? This is h of x, f of x over g of x. And this part is the g of x. Okay, so cleaning this up a little bit, I get x times 1 over root 2 pi and e to the negative x squared over 2 plus 2x. Okay, and here where x is drawn from the exponential with lambda equal to 2. Okay, and then so to estimate this, to get an estimate, is we will draw x from the exponential with lambda equal to 2, and then we apply this function to all of those x values, and then we take the sample mean. Okay, so we draw x from exponential with lambda equal to 2. We apply h of x, f of x over g of x to all our sampled values. And then we take the sample mean. Okay, so let's try this out. Okay, so 0.798, I don't know what that is. All right. Folded normal, but we pretend that we cannot sample from f of x directly. Okay, so h of x is just x. I'm sorry, this is a function of x, or we should just return x. F of x, so not h. H is a function, f is a function of x, and we return 1 divided by the square root of 2 pi times e to the negative x squared divided by 2, and g of x is a function of x, where we return 2 times exp of 2 times x. Okay, so I mean, here I'm just doing it directly. Okay, so we're going to say x is coming from random exponential. I mean, we could just do a random uniform and apply a log function to it to get random exponentials, but we'll just say Actually, let me look up. Rate is 2. Okay, so we'll ask for 1,000,000 values, and we'll say rate equals 2. Okay, and then we'll call these HFG is going to be h of x times f of x divided by g of x. And then we'll take the mean of all of these values. Oh, that's not correct. Did I do something wrong here? E to the negative x. What's that? Oh, this is negative, right? Lambda e to the, yeah, okay. That'll make a difference. And I'm still getting something wrong. The mean of the f is 2 times this. That's why. Okay, that'll. Got to read my own notes. Okay. All right. Okay, and now we get values that are very similar, right? So this was when we did it directly, and then here we're using h times f times g. All right, h times f divided by g, and then we estimate those two, and we get the mean, and it's very similar. Okay. All right, is this okay? And so this is quite useful. Okay, I mean it might not seem impressive right now because we're just doing these kind of silly contrived examples, okay? But there could be situations where you want to get the expected value of some distribution, and that distribution could be crazy, right? And to calculate, so our traditional methods, the analytic methods, require a lot of integrals, and it's not easy, right? So if you said we need to integrate from 0 to infinity this function, that could be a challenge. Maybe it's not too hard, or maybe it is, and so you'd have to integrate this, and that can because the computer is very good at getting generating random values for us, we're able to get good estimates of the numbers that we're looking for. That'll give us these kind of good estimates without having to do the complicated math. Okay, and that's really kind of at the heart of Monte Carlo methods, is that at some point the math gets too complicated. In all of these examples that are kind of simple examples for class illustration purposes, the math might not seem too hard, but we can imagine situations where the math does get messy. Or can I throw this? I'll just throw them right here. Okay. Where the math does get messy, this allows us to, get answers just by using the power of the computer, by using its random sampling approach for us. Is this okay? Let me do kind of just a brief comparison between. There's certain concepts that are similar between rejection sampling and importance sampling. You both have this f of x over g of x term, but they are different, right? Okay, so let me okay. So for rejection sampling, okay. I mean, the biggest difference is that the goals are different. In rejection sampling, the goal is we want we want a random sample of values of x drawn from f of x. Okay, that's what we want. We want a random sample of values of x drawn from f of x. That's the goal of rejection sampling, okay? This part is similar, right? We can't, or it is difficult to draw samples directly from f of x, okay? So instead, we draw values from g of x and propose them, okay? So we draw a value from g of x and we propose it, and then we will either accept or reject this value of g of x based on the ratio f of x over g of x, okay? Or reject, throw away the values. So accept or reject, basically throw away the proposed values based on the ratio f of x over m times g of x, okay? With importance sampling, which sampling is not probably the best term, like a weighted Monte Carlo estimation is probably a better term. The goal is we want to estimate the expected value of a function h of x applied to a variable defined by the PDF f. Okay, so we want to estimate this thing. Okay. Okay. The expected value of a function applied to a random variable with PDF f of x. Okay. Normally, we would draw samples from f of x directly, apply the function, and take the mean. Okay, and that's the most straightforward approach. The trouble is we can't draw samples directly from f of x. And instead, we draw values from g of x. So this part is the same. Let's see, can I copy this? This is what I want, okay? Okay, we can't draw samples directly from f of x. We draw values from g of x, okay? But instead of accepting or rejecting, is now we weight the h of x with the term f of x over g of x. Okay. So there's similarities in that we have a distribution that we can't sample directly from, and so we use another distribution, a g of x. Okay. And with rejection sampling, we either keep or we throw away those values based on this this kind of acceptance ratio. With importance sampling, the goal is not to get a random sample, but to estimate, the value of a function. And so here, we're going to keep all the values drawn from g of x, but we weight them differently. Some of them we weight less, some we weight more, so on and so forth. And we weight them with the term f of x over g of x. Okay. Are there any questions here? We're good? All right. Okay. You guys have, in 1 week, you have a midterm exam. Okay. I know it goes so quickly, right? It's second week, and then third week is halfway through. Okay. So the midterm, I'll say, will cover up through today's material. So I'll cover stuff on Tuesday, but I won't test you on that on Thursday, okay? Because I feel like, that's probably not enough time for it to fully soak into your head. So I'll talk a little bit about the midterm exam, but basically, the midterm exam will cover everything from the first day up through everything we covered today. Okay, so let's talk about midterm exam. Covers from day 1 to today, which is really only day 4, right? It just we're trying to fit 10 weeks of stuff in 12 sessions, 2 of which are tests. So 10 sessions. Okay. So anyway, that's what we've got. All right. So let me think. I wrote some notes down here. All right, so that will be, I guess, third week Thursday, right? Okay, it'll be handwritten. It'll be, yeah, okay, all right. We'll start off, the first topic was inverse CDF method for generating a random variable. So basically I give a PDF, and then you find the CDF, and then you invert the CDF, and then and use the inverted CDF to turn U, drawn from uniform 0, 1, to X. All right. So probably be a continuous case and a discrete case. Okay. And then for this part, use the inverted CDF to turn U, drawn from uniform 1 to X. You know, I will provide U, and I will ask, you know, what X does this correspond to? Okay. So we have the continuous case and we have the discrete case. I don't know. Students complained to me last time I taught this class that the PDF I gave was like too hard. It wasn't. It was, but they complained, right? So it was it was a piecewise linear function, okay? And I think it's completely reasonable, but you know, I might give you, so here's an example. I don't know. What if you had what if this was your thing, right? So it went from 0 to I don't know, 2 to 4, and so this has to so this has a height of 1/4. Okay, so what is that? That's from what is the function here? So f of x is defined as negative. It's going to be 1/4 minus 1/8 x for x on 0 to 2, and then this is going to be negative 1/4 plus 1/8 x for x on 2 to 4. Okay? I don't know. This is not going to be the thing, right? Did I mess something up? Oh yeah, okay, so this needs to be 1/2. All right, thank you. That's good. All right. So what is this? 1/2. Okay, so 1/2 minus 1/4 x, is that right? 2 times, yeah, okay, and then this is negative 1/2 plus 1/4 x, right? Okay. Good. All right. So this integrates to 1, and then so this might be your PDF, and then you have to integrate this to get your CDF, and then you invert that. I guess that part gave people problems because they didn't know how to invert a piecewise function. But okay, so I'm giving you like, I'm giving you too much information here. But anyway, try this out, right? Okay, so do that. All right, and then I might give you a discrete case thing. Okay. I'm not going to give you an example there, right? The discrete case, I'll just say, it's defined by this function, or maybe it'll be a table, okay, of discrete probabilities. And then you find the CDF. When you invert the CDF for a discrete thing, you end up having to make like a piecewise table, right? It's not. It's hard to write a mathematical function that. I guess you can do like floor math, but just make a simple table. That's fine. Okay, that's fine. All right. So discrete case, you can make a table for the CDF. CDF and CDF inverse. Okay, you don't have to do use floor symbols or something. Okay, so that's inverse CDF, and then you would have we're covering everything, right? Okay, so then we'll have rejection sampling. Okay, so I will provide the PDF of the target distribution. Okay, and I will also give you a proposal distribution. Okay, and you will need to find the appropriate M, right? Okay, and then you'll need to find the expected acceptance rate. And then I will, so your target distribution f of x and g of x, okay? And I will provide a proposed value y drawn from g, okay, from the proposal distribution. I will also provide a u drawn from uniform 0, 1, okay? And then you tell me if we should accept or reject y. Okay. All right, so far so good. Okay, and then we'll do bivariate normal. Okay, so I will give a desired u and sigma, okay, and you find B and A. So this should be easy, right? And then I will give Z1, Z2 drawn from the normal distribution, and then you find the corresponding x1, x2, which comes from that, right? All right, and then we'll have Monte Carlo integration, and then we'll have an importance sampling, basically covering everything, right? So, okay, so I'll provide okay, yeah. I'm debating how I should do these ones. I think, so I'll provide h of x, okay? And then I'll provide values drawn from a distribution. So this is going to be like very bad integration or importance sampling, right? Because when we do integration, we're going to have to do, you normally ask the computer to do like 1,000,000 random values. I'll provide values drawn from a distribution, but I'll probably give you like 4 values, right? Because I don't want you to have to do 1,000,000. So, but I'll give you like, maybe like 4 values drawn from some distribution, okay? And I'll decide whether it's Monte Carlo integration or not. This will be, importance sampling or not. So maybe from F, maybe from or G of X, okay? And you'll have to figure out what to do next, all right? So I'll provide values drawn from a distribution, and then I'll ask you for the expected value of this, using the random values. Okay. Is that good? Are there any questions on this? Okay, so you have a week to prepare from now until then. You also have a homework due, but I think the homework will be helpful in your studies and preparation. And then we'll start new material on Tuesday, but that will not be covered on the exam. That's 1 week from today. Okay. All right. We'll end here for today. Have a great weekend. We'll see you guys on Tuesday.